is part of the BocaPhysics series on electromagnetism. In today's lecture, I'm going to discuss the multipole expansion of the magnetic vector potential. If you recall back in electrostatics, we covered the multipole expansion of the electrostatic potential. And in that case, we used an expansion and basically came up with an expression in terms of Legendre polynomials. As you'll see, we'll follow the same kind of treatment here. So let me begin with the magnetic vector potential. That's equal to mu naught over 4 pi, line integral of the current divided by the magnitude of the separation vector. Back to electrostatics, just as a reminder. The potential is equal to 1 over 4 pi epsilon naught volume integral of the volume charge density over the magnitude of the separation vector. Okay, so sketch out a loop here. As is usually the case, R prime represents the source vector. And R represents the field vector or observation vector. Our goal here, just as with the electrostatic potential, is to derive an expression for the magnetic vector potential that is valid for distant currents. So we call this angle here theta prime. I can write this magnitude as 1 over the square root of r squared minus 2r r prime cosine theta prime plus r prime squared. Now, since we've already covered the mathematics here, I'm not going to write out all the gory details. I'll merely quote the result that this can be written as one over r summation n equals 0 to infinity of r prime over r to the nth power times the nth order Legendre polynomial as a function of cosine theta prime. We are interested in distant circuits. In each case, it is certainly true that R is greater than R prime. Okay, so observation or field vector is greater than the source vector. Let me insert this expansion into the expression for the magnetic vector potential. So we begin here with the monopole term. This term always vanishes. And the reason why it always vanishes is because there's never been a magnetic monopole observed. Basically, this is an expression of the fact that the magnetic field is divergence free. And that holds not only in magnetostatics, but also for time-varying fields as well. This is a dipole term. And it is the dominant term in this expansion. We go to higher orders, you have quadrupole, octupole, and so forth. But we're going to focus our attention on the dipole term. It's equal to mu naught I over 4 pi r squared, line integral of r prime cosine theta prime. Okay, so theta prime is the angle between r and r prime. Therefore, I can rewrite this as r dot r prime dl prime. And notice that because of that, this r, I've divided through by the magnitude of r as well. So basically, this is just the r caret direction of the field vector dotted into the field source vector. Okay? Now you need to go back to vector calculus to realize that this is the same thing as this. So basically, this is just giving us an area, and it's actually minus r crossed the area enclosed by this loop. If I define m equals to current times the integral, basically the area, and I'm just going to drop the prime here for now, I can rewrite this dipole expression as mu naught m cross r over 4 pi r cubed. So that is the leading term in this expansion. You might ask yourself, well, is there such a thing as a pure dipole? And how could I come up with that? Well, what you have to do in that case is basically hold this constant, hold the magnetic dipole moment constant as you let the current get infinitely large, and then you will have an expression that holds for a pure dipole. Let's suppose that this pure dipole points along the z-axis. So therefore, I can write the magnetic vector potential, the dipole, as mu naught m sine theta over 4 pi r squared in the phi direction. I want to go one step further and figure out what the magnetic field is. And I'm just going to rewrite this expression up here first. And the curl of the magnetic vector potential gives the magnetic field, which in this case will be mu naught m over 4 pi r cubed two cosine theta in the radial direction plus sine theta in the theta direction. Okay, let's look at an example. I'm going to work out a few examples. Some of them I will work out all the way. A few of them I'm just going to give you the setup for it and so that you can work through the problems the rest of the way yourselves. Okay, so let's take a current carrying ring of radius r. Magnetic dipole moment, in this case, is readily calculated. It's just equal to the current times the area, pi r squared. And in this case, it's pointing in the z direction. So I can just plug this into here to find an expression for the dipole. So this is mu naught I over the radius of the ring squared times sine theta over 4 r squared, where r represents the observation point, and that's going to be way out here somewhere. And this is in the phi direction. Magnetic field now due to this dipole, and let's suppose that we are interested specifically with the dipole along the z-axis. In this case, you look at my expression, and along the z-axis corresponds to theta equals 0 degrees. So this term drops out, and well, this cosine 0 is just, of course, 1. And you find that that's equal to mu naught I r squared over 2 z cubed in the z direction. Now, if I compare this with the expression we derived I should say exact expression for the magnetic field due to a current carrying loop, well, with mu naught I r squared over 2 z squared plus r squared to the 3/2 power in the z direction. Now, if I take the limit that z is much, much larger than the radius, that's what we're doing after all when we're looking at the multipole expansion. We're interested in the expressions valid for distances much greater than the magnitude or dimensions of the loop or whatever you're looking at. So if z is much, much larger than r, this collapses to the expression I get with using the magnetic dipole moment. Okay? Let's look at another example. Let's say that you have a disk. And that disk carries uniform surface charge density sigma, and it spins with angular speed omega. I want to figure out what's the magnetic dipole moment. So, what's M? Rather than starting from scratch, I'm going to kind of use what I know about dipole moment due to a ring. Okay? So, in this case, we got to consider not just ring of radius capital R, but we got to go from R equals 0 all the way up to the radius of the disk. I've got to just look at a ring inside of that disk. Okay? So this is R here. Figure out how much charge is contained within that ring. Charge contained within that ring is just equal to surface charge density times the area of the ring. Well, the area of the ring is just 2 pi r. That's the circumference times the thickness, which is dr. Well, I need to know what the current is, so not only do I need to know the charge, I need to know the increment of time. And dt is equal to the time it takes to make one revolution, or 2 pi over omega, so therefore, the current is equal to sigma omega r dr. So, surface charge density times angular speed times the radius times that thickness, okay? So I know what the current is, and then I also know the area as well, so I'm going to have to integrate this. And therefore, M is equal to sigma omega r dr, and also times the area of the ring, which is pi r squared. Integrate from 0 up to r. I'll be left with pi times sigma omega r to the 4th power over 4 and that'll be in the z direction. That's the magnetic dipole moment due to a disk. I want to go one step further, and I want to figure out, well, what's the dipole moment due to a spherical shell? Charge density, sigma, and spins with speed and angular speed, omega. So again, you always want to use what results that you've already obtained to arrive at a solution here. Well, let me sketch out this problem. And I'm going to basically calculate the contribution from each of these rings. Essentially, this just amounts to integrating all the way from 0 to pi. How do I change my results so far? Well, I'm going to need to replace the radius by sine theta. So I've got my current is going to be sigma r sine theta. And this time the thickness of the ring is r d theta. This is the expression for the current that flows, or actually what is the same thing, the current that flows around the surface, essentially. Or that we can think of it as flowing around the surface. I guess is a better way of putting it. Okay, so that's a current. What about the area of this ring? Well, let's just equal pi times the radius of the ring squared. Well, in this case, the radius of the ring is not just r, that's the radius of the sphere, it's r sine theta. So from here over to here. And if I take the product of these two, that'll be the contribution to the magnetic dipole moment dm. But then we need to integrate from 0 to 0 to pi to take account of all the rings. So we're integrating from here over to here. It's instructive as well, once you come up with the expression for the magnetic dipole moment, to go ahead and plug that into this expression, figure out what the magnetic vector potential is, and then also look at, well, what's the magnetic field. Another problem that you might want to work out is that, let's suppose instead of having a spherical shell, you've got a uniformly charged sphere. And again, it spins with angular speed omega. But this time you have rho instead of sigma. So how do you use what you've calculated before in here? Well, once you crank everything through, do the math, you'll have an expression that's in the terms of has radius r appearing in the expression, and also sigma. So, since you need to take account of everything inside the sphere, not just what's on the shell, let's say that you substitute for sigma rho dr. And let's suppose further that you replace r by little r, and you want to integrate. And here you're integrating over the polar angle theta, and over here you're integrating over the radius. So leave this up on the board for a minute so that you can take everything in. We've worked 2 examples all the way. 2 more. Basically what I'm doing, I'm using what I've already calculated, the framework, and applying it to a spherical shell with surface charge density sigma, and then taking this result and figuring out what the magnetic dipole moment is due to a uniformly charged sphere. So again, it's instructive here to calculate what the magnetic vector potential is and the magnetic field is, and compare that with the exact results. Okay? I have one final example that I'm going to go over. In this case, I will work it out all the way, since it tends to be a little bit more, work to arrive at a result. Okay, so I probably left it up there long enough, and I will erase. In this final example, I'm going to calculate the magnetic field due to a cylinder that bears uniform surface charge density sigma and rotates with angular speed omega. Orient the axes such that the z-axis goes up and down, positive x points to the right, and positive y is going to point into the board. Now, I don't want to calculate the magnetic field everywhere, I just want to calculate it at the mid-plane. So in other words, we want to know what the magnetic field is for z equals 0, and also at distances much, much greater than r. So in other words, our field point, observation point if you prefer, is much, much larger than the rates. It's, the observation is much, much greater than the dimensions of the problem. If I can do that, I can exploit magnetic dipole to handle this problem, to model this problem. So in other words, what I can do is I can treat this cylinder, as essentially a stack of current-carrying rings. Basically, a bunch of little dipoles stacked up. If I do that, and just as a reminder, the magnetic dipole moment due to a current carrying ring is just I pi r squared. Magnetic field due to that dipole is equal to mu naught m over 4 pi r cubed 2 cosine theta in the r direction plus sine theta in the theta direction. It's convenient to convert these unit vectors to Cartesian unit vectors. So in other words, we'll write this as mu naught m over 4 pi r cubed been doing throughout the semester to make the problems a little bit less complicated to handle. We've exploited the natural symmetry of the problem. If I look at any place in the xy plane with these s much, much greater than r, what I can see here, in fact, even if we don't assume s is much greater than r, the magnitude of the magnetic field is going to be the same. There's going to be the same kind of behavior there. So it doesn't matter where what phi I choose. I could just choose phi equals 0 because I know my result, my final result, can't depend on phi because of the symmetry, and that's going to eliminate the y direction terms. to next? We should sketch out my dipoles. And just make believe these are nice little, nicely drawn rings. Okay, so anyway, this is the z-axis still. This is the x-axis. And no, this isn't drawn to scale. S is much, much larger than the dimensions. So anyway, we'll call this angle theta here. And we'll say, well, this corresponds to some distance minus z. What happens, because again, because of the symmetry of the problem, I'm going to have as many dipoles above, as many contributions above the z equals 0 plane as below it, and those are going to be pointing in opposite directions. So this x term is just going to drop out, and I'll just be left with a z contribution. Now, I'm not just looking at a single dipole, I'm looking at a whole stack of them. So it's actually more convenient to think of a magnetic dipole moment per unit length. Here I've just replaced sine squared theta by 1 minus cosine squared theta. So I'm taking care of the minus signs. You're left with 3 cosine squared theta minus 1 over r cubed. Now, what is the magnetic dipole moment per unit length? Well, if you just had a single ring, it would just be I times pi r squared. In this case, because you've actually got a cylinder that's rotating, this is sigma omega r times pi r squared. Okay? So basically, this is a current per unit length. And the reason why I have to do that is because we're going to integrate over all of those infinitesimally small dipoles. Okay? That pi will cancel with that one. Also, because I can just multiply this by 2 and hence integrate from 0 to L over 2. And now you see the problem here. We're integrating over z coordinate. However, I've got cosine theta inside the integrand and r inside the integrand. They're all related to each other. I have to write everything in terms of one variable. S remains constant. That's just the field point. That's not going to change. We're not integrating over that. So let's make the observation that S is equal to r sine theta. Just follows immediately from the geometry of this problem. S is the opposite side, so sine theta gives me opposite over hypotenuse, and therefore r cubed is equal to s cubed over sine cubed theta. How about Z? Z is equal to minus S cotangent of theta. Again, follows just from the geometry of it. I want to know what dz is equal to because that's what's in my integral. S is constant, so that doesn't, we don't differentiate that. With a little bit of manipulation, that's equal to S d theta over sine squared theta. I'm going to plug these into here. And also my limits are going to be written in terms of theta as well. What does z equals 0 correspond to? Well, that corresponds to theta equal pi over 2. So that's my lower limit. L over 2, for the time being, we'll just call it theta top. Okay, so basically we're going to integrate from here, here, all the way up to here, and I'll call that angle theta top. Making these substitutions, and actually that pi should not be there. Okay, so this is sigma naught omega of permeability times the surface charge density times angular speed times the radius of the cylinder cubed over 2, integrate from pi over 2 to theta top. And this is 3 cosine squared minus 1. 1 over r cubed, that gives me s cubed over sine cubed theta. And dz gives me should be it. The other way around would be sine cubed theta over s cubed down there. And dz is going to give me s d theta over sine squared theta. Okay, so this is mu naught sigma omega r cubed over 2s squared. When I evaluate cosines at pi over 2, that's obviously going to be 0. And here what I've done, I've just factored out cosine theta, so basically you're left with the product of cosine theta times 1 minus sine squared theta, and there should be a minus, nope, not yet. So this is sine squared theta top cosine theta top that we're left over with. Now, what's theta top equal to? Well, let's look back at the diagram here. This is theta top up here, so therefore, and I'm running out of space, but sine theta top is equal to s over square root of s squared plus all squared over 4 cosine theta top is equal to minus L over 2 square root of s squared plus L squared over 4. Again, look at the geometry here. This is L over 2 here. This distance is s, so it's opposite side over hypotenuse and adjacent side over hypotenuse. But again, we're looking at this angle here instead of this one here. This is why you've got a minus sign in your cosine term. So plugging everything in, final result is minus mu naught sigma omega r cubed L all over 4 s squared plus L squared over 4 to the 3/2 power. So that is how you figure out the magnetic field due to a spinning cylinder that bears a uniform surface charge density and rotates with angular speed omega. And I'll just leave this up on the board. Again, this is another example of going from a simpler problem to actually a difficult problem. And just by treating it as cylinders as static dipoles, we're able to come up with a closed form expression. And by the way, this is pointing in the z direction, and don't want to leave that off, okay? And that concludes today's lecture.